Okay, we're going to do second day of regression notes and talk about a least squares regression line. So let's start with some definitions. Okay, bivariate data means that we have two variables. The x variable is the independent or the explanatory. The y variable is dependent or the response variable. And we use x to predict y. So least squares regression line has this form: a y hat equals a y-intercept a plus bx. So I relate this to your slope-intercept form way back in algebra. So y hat means that it is predicted. Okay, so if it has a hat on it, it means it is predicted. It's not the actual value, it is a prediction. Yes, I have to put the hat on it. Okay, if you don't put the hat on it, it means that you're actually talking about the exact data point and not a predicted data point. B is your slope, rise over run. It is the amount by which y increases when x increases by 1. So again, rise, y over run, x. And A is your y-intercept, where it crosses the y-axis, or the value when x is 0, your starting point. It is the height of the line when x equals 0. And in some situations, it could have no meaning. Since we're dealing with real-world data, oftentimes there's sometimes where we can't deal with negative numbers, and so the y-intercept wouldn't actually have a real-world meaning. So least squares regression line, abbreviated LSRL, gives the best fit to the data set. It is the line that minimizes the sum of the squares of the deviations from the line. And here's how we do it on the calculator. I'll show you an example in a minute. You enter your data in your list and spreadsheets. You click menu, statistics, and len reg, and always mx plus b. Your output will then give you your b equals to plug in your slope, or your m equals to plug in your slope, and your b equals to plug in your y-intercept. So let's visualize what a least squares regression line is. So we have 3 data points, 0, 0, 3, 10, 6, 2. If I were to have this predicted line, let's say I have the predicted equation line, 0.5x plus 4. Well, we're going to see, is this the best fit? So what I'm going to do is I'm going to take my actual data point of 0, and I'm going to find the predicted y value. So the actual y is 0, but if I use my prediction equation, because it has y hat, plug in 0, we get a value of -4. Therefore, the actual point, because it's -4, it is 4 below the predicted line. So the residual would be -4. Let's do the same thing with 3. If we plug in 3 into our predicted equation, the predicted y would be 5.5. So it is a difference of 4.5. And do the same with 6. We have a difference of -5 because the actual point is below. So if you were to actually square all those and add, we get a value of 61.25. Well, that line looks pretty much in between those data points, but let's see if we can have an even better fit. Well, here we still have these 3 points, but notice we have a new line of predicted line of y hat equals 1/3 x plus 3. Well, let's do the same thing and let's find the predicted y. If we plug in 0, predicted y would be 3. So again, the difference between predicted, actual, and predicted would be -3. Same thing for 3 to 10. We'd get a difference of 6, and for 6, we get a difference of -3. If I square these and I add these together, notice we get 54. Now notice, is 54 smaller than our previous sum from our previous equation? Our previous equation was 61 something, so yes. The least squares regression line is the line that minimizes the sum of the squares. So this predicted equation, 1/3 x plus 3, is a better fit of these 3 points than the previous line. And also how we know is what is the sum of the deviations, okay? I'm going to define definitively what this deviation is just difference from the actual point to the predicted point. If I add all these up, 6, -3, -3, it will always be 0. So how do we interpret our least squares regression line? Well, we first can interpret slope. Think back to algebra. We interpret slope by saying for each unit increase or decrease, depending on if it's positive or negative, for each one unit increase in x, relate to what objects you're talking about. There is an average, either increase or decrease, positive or negative, of b. State the value, state the slope, relating it to y. How do we interpret the correlation coefficient? We did this last notes. There is either positive or negative, weak, moderate, strong, linear association between your two variables. Make sure to relate it to your problem. You need to memorize these sentence stems. If it says interpret slope, this is how you would write it. If it says interpret correlation coefficient, that is your sentence stem. So let's look at an example. How do we put this into practice? Here we have the ages in months and the height in inches of 7 children. Let's find the least squares regression line. So we're going to let the calculator do the work for us. So let me pull up the calculator. Okay, anytime we need to input data, click the home button. We're going to go to list and spreadsheets, which is the Excel looking thing. Very first thing you do is you label your column. So here we have age and we have height. Input your data values. Make sure one of your data values is highlighted. Then we're going to go to menu, statistics, stat calculations, and always linear regression mx plus b. And it's going to ask us, well, what did I call my x list? I called it age. What did I call my y list? I called it height. Again, you can label it according to what you titled it. And don't change anything else. Hit enter. Okay. And notice it gives us output here. If you scroll up to the top, notice it shows you the basic form. Notice it shows us the basic form here, len reg. And notice it gives me my slope. My slope is 0.34. Notice it gives us our y-intercept. Our y-intercept is 20.4. And notice it gives us an R value of 0.99. Another way to find the least squares regression line, you won't find the R value this way, is you can make a scatter plot. If we go to menu and you go to a data, actually highlight a data point, I forgot that. Highlight a data point, then go to menu, data, and then quick graph. Again, the x-axis, we can label it age. The y-axis, we can label it height. So there's my nice, pretty scatter plot. And again, it looks almost like an exact line, which is why our R value was 0.99. From here, you can also find the least squares regression line by hitting menu, analyze, and notice we want the regression. Well, what kind of line do we, it looks like a linear line, so mx plus b. And notice it gives you the equation right here. Y hat would equal 0.34x plus 20.4. So 2 ways to find it. Again, here you don't actually get your R value, which is why you need to do it from the table. Okay. But how do we write it out? Again, if it is a least squares regression line predicted, that is y hat equals my slope is 0.34x plus 20.4. And we always label what is x. X is age in months. What is y hat? Y hat is the predicted height in inches. So how do we interpret the slope and correlation coefficient in the context of the problem? Well, we already said the correlation coefficient here was r equals 0.99. So there is a strong, because it's above 0.8, positive linear association between, what are we talking about? Age and height of children. And how do we interpret slope? Well, this was our regression line. This should be 0.34. For an increase in age of 1 month, there is an appropriate increase of, this should be 0.34 inches in height of children. So make sure that you relate it back to the problem by including age and height. So using that same information, let's predict. The whole point of a least squares regression line is that I can predict future values. So let's utilize, this is the same data set from the least squares regression line we just found, predict the height of a child who is 4.5 years old. Well, again, our predicted equation is 0.34x plus 20.4. Now notice it asks for 4.5 years. Notice that my equation gives the age in months. So how many months is 4.5 years? Multiply it by 12, right? So we're plugging in 54 into our predicted equation. So 0.34 times 54 plus 20.4 gives us a value of 38.76. And that would be inches. And if we were to want to actually see about how tall this child would be, that would equate to 3 feet, 3 inches. So that sounds reasonable. 4.5-year-old would be about 3 feet. That sounds reasonable. Well, let's utilize this prediction equation to predict the height of someone who is 20 years old. Well, somebody 20 years old in months, multiply that by 12, will be 240 months. Well, we get 102 inches. And this person at 20 years old would be 8 feet 6 inches. 8 feet 6 inches. Well, what is wrong with that? Are we really going to have somebody 8 feet 6 inches? I mean, maybe if they're in the Guinness Book of World Records, but probably not. So why doesn't my equation work? Notice here that we were finding the height of somebody who is 20 years old. And we said, again, 20 years old was 240 months. Where does 240 fall in our data set? 240 is significantly higher than any of our other data points. So extrapolation is when the least squares regression line should not be used to predict y's for values of x outside the data set, okay? It is unknown whether the pattern observed in the scatter plot continues outside this range. So notice in the previous example, I only have from months 16 to 120. So this prediction line only is a good predictor between months 16 and 120. I'm trying to plug somebody in that is 240 months old is not going to work, because what happens as we get older? Eventually we stop growing, right? We're not going to grow at the same amount all the way till forever. Right? Once about 20 years old, we stop growing in height. You probably grow wider, but you probably stop growing in height. So past adult years, we're not going to have this same regression equation. We're going to need a different one. Okay. So extrapolation means you should not predict outside of your min-max range. So the only months that we can predict is between 16 and 120. And that's called extrapolation. Correlation coefficient and the least squares regression line are both non-resistant measures. They're both non-resistant measures. Okay, remember non-resistant means that they can change. If I add in an outlier, possible outlier, it's definitely going to change even adding one value will significantly change R or the line. So to define residuals, we talked earlier about residuals. First off, the residuals, by definition, is the difference between an observed value and the predicted. So it's observed minus predicted, or Y minus Y hat. Positive residuals are above the line. So if you get a positive, that means that the data point is above the predicted. If you get a negative residual, it means the data point is below the predicted. And the sum of the residuals, if it is the least squares regression line, the best fit, it should always be 0. Because if this line is smack dab in between all the data points, then I should be able to add all these distances and subtract all the negative distances, and it should sum to 0. So always sum to 0 for the line of best fit. Because basically what a residual, yeah. The key is observed minus predicted, observed minus predicted. So what is a residual plot? A residual plot is a scatter plot of the x, comma, residual pairs. Residuals can be graphed against other statistics besides x. Most commonly, it will be x. And the purpose is to tell if there is a linear association existing between the x and the y. So a residual plot is basically just taking that least squares diagonal line and turning it horizontal. Okay, so you're taking your diagonal least squares regression line and you're taking that line and you're making it horizontal. And what we want to look for is if that line of best fit is exactly smack dab in between your data points, there should be no pattern existing between the points. And if no pattern exists, then we can say the association is linear. So let me show you an example. Here we have a residual. Again, just think of this x, the line of best fit would typically be diagonally, and we're just taking that diagonal line and zoop, making it horizontal. We should have half above, half below. If it's random, that means it's linear. If it's not random, that means that this line is not in between all those data points. It is not linear. And how we find those actually on the calculator, I can show you from this last example. Again, if you want to find the residual plot, click on the graph, go to menu. You have to first do the least squares regression line. And once you have the least squares regression line, you'll have access to this residual button. And you can click residual, show residual plot. And notice all it's doing is taking this line and zoop, making it horizontal. Takes this line, makes it horizontal. So notice half your point should be above, half your point should be below. So no pattern means linear. So least squares regression line. Line of y on x is a line that makes the sum of the squared residuals as small as possible. So this is by definition. And we showed you this example through the 3 points with the line in between. And lucky for us, calculator will spit out the answer. Just make sure you know how to format it. And that concludes least squares regression line notes.